Hello everyone. My name is Xingyu. I'm currently a postdoc at the Harvard University. Today, I'm presenting our paper, a safety framework for critical systems utilizing deep neural networks. This is a joint work between the Harvard University, Defense Science and Technology Lab, and the University of Liverpool. This work is essentially about an initial idea on how to build a quantitative safety case for systems utilizing deep neural networks. This is my today's agenda and also a quick overview of the paper. I will first very briefly mention the preliminaries on safety case and goal structuring notation, machine learning lifecycle models, and what is the generalization error that used as a primary quantitative measure in this framework. Then I will present the top-level safety arguments, which is basically about how to obtain or decide the high-level quantitative claims in this work. And we use the reliability property as an example. Then I will present how to support these reliability claims with lifecycle assurance. That is, we try to map each machine learning lifecycle activities to some confidence bounds on the different types of generalization errors. Then we treat this set of confidence bounds as prior knowledge to do conservative Bayesian inference to update our beliefs on the generalization error when seeing some operational testing data. Finally, we discuss and conclude the work. Despite the wide applications of deep learning, new features of deep learning, like the black box nature, increase apparent non-determinism, which we believe, on the one hand, emphasize the role of using probabilistic measures to capture uncertainties, but on the other hand, makes it quite hard to estimate those probabilities. And recent progress has been made to the verification and validation of deep learning. Well, these new techniques are not only able to support low-level claims like the local robustness of a deep neural network. We are still unclear about how to build up confidence in some high-level safety and reliability claims. So these two facts motivate this work. We investigate how to argue deep learning safety in a quantitative way and try to organize different types of evidence like formal verification and operational testing to support high-level claims. For preliminaries, first it's about what are safety cases and the goal structuring notation. In short, a safety case is a structured argument supported by evidence intended to justify a system is safe for a given application in a specific operating environment. And the goal structuring notation, we say GSN for short, is one of the most popular notations to present a safety case. And I'm showing some very basic elements of GSN. You can see the goal here represents the claims, strategy represents the arguments, and solution means the evidence. We also have a very quick example of a safety case, but I guess the audience should be very familiar with them, so I will just skip the details. There are many studies on some comprehensive machine learning lifecycle models. Well, here we simply refer to a typical one that includes initiation, where you need to consider if a deep learning model is needed at all. If yes, what platform to use. Data collection, model construction, where we need to consider how to decide the best architecture of the deep learning model. Then is the model training, analysis of the trained model, where we normally do the verification and testing. And finally is the runtime reinforcement, like the operational monitoring and testing. For a machine learning model, we normally can define different types of generalization errors, depends on the loss function we use. In this work, we assume a 0-1 loss function. Therefore, the generalization error here means the expected probability of seeing a wrong output given a randomly selected input from some operational profile. I'd like to note this 0-1 generalization error is equivalent to the common seeing reliability measure, probability of failure per demand, we say PFD for short, that defined in some safety standards like IEC 61508. And we will use these two terms interchangeably in our safety arguments, depends on the context. This is our top-level safety arguments. Essentially, we try to argue that the deep neural network is safe enough over all safety-related properties. And the list of all those properties of interest for this given application can be derived from approach like property-based requirements. As an example, we discuss in the paper how to determine the reliability claims. Well, the general idea holds for other properties as well. To decide the top-level reliability claims, we need to answer three questions. First, what is the appropriate reliability measure for the given application? For instance, a spacecraft could be very reliable in terms of failure rate per mile, or very unreliable in terms of failure rate per mission. Well, in this paper, we use the probability of failure per demand, PFD, as an example for the deep neural networks dealing with, say, images, where each image is an input demand. Second, what is the quantitative requirement stated in that reliability measure? That is a upper bound on the PFD in our example, meaning our PFD cannot be worse than something. This is not an easy question. Normally, the answer depends on the system architecture. We need to break down the reliability requirements from some higher level systems according to that architecture. And we identified some open challenges here, like you need to consider the failure dependencies between the channels if it is a 1 out of 2 system. Finally, it's about how to gain confidence in that claim. Reliability measures like PFD normally concern system behaviors subject to arbitrary uncertainty. Well, due to the imperfect knowledge of human assessors about the system, we cannot be certain that the PFD is indeed smaller than that required bound. And we normally have some doubts about that. And we need to quantify this doubt, this confidence in that claims as well. Next, we will see how to boost this confidence from assurance activities in the machine learning lifecycle. This is the safety arguments we developed for the reliability claim, where the upper bound on PFD is derived from higher level systems. And we argue there is a sufficient confidence on the upper bound by using a Bayesian statistical inference approach called conservative Bayesian inference, and we say CBI for short. Essentially, CBI takes partial prior knowledge from lifecycle activities and Bayesian update our beliefs on reliability when seeing some operational data. And of course, some assumptions used by CBI, like a unchanging operational profile, need to be assessed in the safety case and keep monitored during the operation. To be exact, now let's have a look at the gist of CBI using a quick example. Say x is the random variable representing the unknown PFD, and fx is the prior distribution of this unknown PFD, and the p is a given upper bound on the PFD. That is, our PFD cannot be worse than this upper bound. Then, after seeing k failures in n tests, we can simply write down the objective function as the equation 1 by the Bayes theorem. Essentially, this equation 1 is about a posterior confidence bound on this given P. Well, instead of assuming a complete prior distribution for f of x, CBI only requires some very partial prior knowledge, like the one in this equation 2, which is basically a piece of confidence bound on PFD. Then CBI solves a optimization problem of what is the prior distribution f of x that minimize the objective function 1 subject to the constraint equation 2. We are minimizing this objective function 1 here because this is the practical meaning of being conservative, and the equation 2 is a piece of partial knowledge in the sense that it is far from the complete prior distribution. Rather, it is just some constraints on the prior distribution, and we know there is a set of infinite numbers of prior distributions satisfying this piece of partial prior knowledge, and we try to find out in this optimization problem what is the corresponding worst case prior distribution in this set that gives you the minimized objective function 1. And once we got this worst case prior distribution, we can easily get the worst case posteriors by the equation 1. What I have just presented is only a simple example of CBI. CBI is actually a set of theorems allows the reasoning for different forms of posterior objective functions like the posterior expected PFD, the posterior confidence bound on PFD, or even the future reliability of parsing some demands after seeing the evidence. CBI also supports the use of different types of prior knowledge, like the prior mean PFD cannot be worse than something, or as we have seen, a prior confidence bound on PFD. And also, we can say some prior confidence in the reliability of parsing n tests before we actually do the test. In the paper, we also presented some numerical examples in which the objective function is the future reliability of passing some amount of testing given we have seen some failure-free tests, and the prior knowledge is a confidence bound on PFD. If we have a look at this red dot on this solid curve, a possible scenarios could be before the testing, I have 90% confidence that our PFD of this software cannot be worse than 10 to minus 5. The reason behind this could be I have developed this software strictly against to the safety integrity level 4, and based on some statistics that all 90% of the software developed against sales level 4 and passed the certification can achieve this level of reliability. Then after seeing some failure-free testing like 10,000, then we can almost be 99% confident that our software will survive the next 1,000 tests. In summary, CBI is the fundamental statistical inference argument in our safety case. Instead of assuming a complete prior distribution, CBI is a optimized Bayesian inference approach using the worst-case distribution for the given objective function subject to some partial prior knowledge. Here, these partial prior knowledge are actually the constraints used in this optimization problem. And we believe CBI has some unique advantages like partial prior knowledge is much easier to get and justify in safety cases. Well, a complete prior distribution normally assumes extra and unjustified assumptions, and this extra information normally lead to optimistic bias in the reasoning. Also, CBI can guarantee on some conservative outcomes because CBI is a set of proved theorems for the given combination of objective function and constraints. Now the question becomes how to get the partial prior knowledge on PFD, which is also the generalization error defined in terms of a 0-1 loss function. First, let's see a known result of decomposing the generalization error, as shown in this equation. From right to left, the first one is the so-called Bayes error, which is non-zero if the ground truth label is not deterministic. For instance, an image could be labeled as wolf by one person and also labeled as dog by another, and both of them believe their labels are the ground truth. So intuitively, this error captures the uncertainties in the dataset and the activities in the initiation and data collection stages in the machine learning lifecycle are trying to reduce this error. The second one is the approximation error of a set of DNNs. That set is determined by the architecture of the DNN, like the number of layers and the choice of the activation functions. Therefore, intuitively, this error is measuring how good our hyperparameters of this DNN, and this error can be reduced by activities at the model construction stage. Finally, the third one is the estimation error of a trained DNN. Essentially, this error measures how far is the trained DNN from the best one in the set of DNNs that having the same architecture. In other words, it's about the training and optimization of the DNN given a architecture. So this error can be reduced at the model training and analysis of a trained model stages. Now let's see a simplified example of how to get a confidence bound on the 0-1 generalization error, like this equation 3, from the robustness verification in a one-dimensional input space. Essentially, robustness verification assures us that for a given input represented by those blue triangles in the figure, all its neighborhood inputs represented by those green squares on the black line are having the same and the correct label. Then the upper bound epsilon is essentially the ratio of the length not being covered by the green regions to the total length of the black line. That is intuitively the probability of randomly select input on that black line will not fall into those green regions. Okay. Of course, there are some underlying assumptions for those robustness verification results, like we need to assume all the inputs inside a green region are actually sharing the same ground truth label, which is questionable, of course. And second, we might need to assume the verification tool itself is perfect, which may not hold. So the confidence in these underlying assumptions are actually we need to capture them by this parameter theta. Now you may ask how to assign numbers to this theta. Yes, that's a hard question, and in the paper we identify this problem of quantifying the doubts in formal verification as an open challenge, and we believe the answer relates to scientific ways of eliciting expert judgment, and we also need to do statistics on the reliability of verification tools. However, we believe the evaluation of confidence in the evidence or assumptions in safety case arguments is not unique to our approach. Rather, it is a generic challenge for all safety case approach in which you need to either do the evaluation in a qualitative way or in a quantitative way. To conclude, in this work, we target at the quantitative high-level claims for deep neural network safety, and we emphasize the use of probabilistic measures to capture the inherent uncertainties of deep neural networks. The confidence in those claims is updated in a Bayesian way when we see some operational data collected from the continuous monitoring after the system has been deployed. The update guarantees to be conservative, subject to some partial prior knowledge obtained from other machine learning lifecycle activities. We agree with other researchers' opinion that a credible safety case requires a heterogeneous approach, and we had a first try in this work to combine the proven in use and field testing arguments, verification and validation arguments, and other process-based arguments. Because of the open challenges we identified in this work, we didn't do a practical case study, which forms our important future work. That's all for my today's presentation. If you are interested in this paper or you have any questions, please feel free to contact me by dropping me an email. Thank you.